The High Flux Isotope Reactor at Oak Ridge National Laboratory will be 60 years old on August 25th, and plans are being made to extend its life to the end of the century, making the reactor more than 135 years old. Wish we could do that for humans. HFIR is remarkable in many ways, including the fact that it was designed by a student, Dick Cheverton, at the ORNL reactor training facility, and presumably he just used paper and pencil and a slide rule. The isotope production and neutron research at HFIR have led to many discoveries and practical applications, including new elements in the periodic table, such as tennessine, life-saving medical advances, improvements in airport and dock security, and nuclear fuel for planetary and space exploration. The reactor is a significant source of critical radioisotopes for the United States. HFIR was even used to cast doubt on a historian's theory that President Zachary Taylor in 1850 died of arsenic poisoning instead of food poisoning. I am pleased to introduce to you Chris Bryan, our speaker today. He is leader of the Radioisotope Production, Engineering, and Analysis section in the Radioisotope Science and Technology Division at ORNL. Chris joined the lab's research reactor division in 2009 after nearly 2 decades leading development of medical and consumer products and industrial equipment. He began his ORNL career by leading a successful effort to increase the use of HFIR's reactor core for radioisotope production and materials and fuels testing. A mechanical engineer with a BS degree from the University of Cincinnati and an MS degree from Ohio State, Chris led the development and quantification of neptunium targets to help enable the eventual first production at HFIR of plutonium-238, and that was back in 2013. ORNL is the source of plutonium-238 nuclear fuel needed to help power NASA's future space probes, and currently, the ORNL product is powering the Mars rovers. In 2020, Chris participated in planning the replacement of the HFIR reactor pressure vessel. He also led an internally funded project to conceive and plan new or enhanced HFIR facilities that could improve ORNL's scientific capabilities during or following pressure vessel replacement. Please join me in welcoming Chris Bryan, who will speak on 60 years of scientific highlights in the research reactor's history and plans for key upgrades. Chris?
Thank you very much, Carolyn.
Here. We don't have audio out here in the audience.
Should these speakers be connected?
They're supposed to be. They are.
No, they're not.
No, they
That's
aren't.
all you get.
Oh, you're gonna have to use your military voice.
I can speak loudly, don't worry. I raised 5 children. I can talk loudly. So thank you for the introduction again. I'm going to cover a pretty wide variety of topics related to HFIR. I'm not an expert at all these things, but I know the experts and I've worked with them and I get a lot of this information from them. And I'm kind of good at, hopefully I'm good at conveying the message of these interesting applications. We'll find out. So I'm going to talk a little bit about HFIR if you're not familiar with it, and some of you may be, some of you may not be. But HFIR was really the brainchild of Glenn Seaborg. Glenn Seaborg was a radiochemist at Berkeley Labs and the discoverer of plutonium and I think 10 other elements or 11 other elements. He pushed the Atomic Energy Commission in the 1950s to build a reactor to make him more material so he could practice his chemistry. He couldn't get enough material. So this was his mission. He didn't make much progress at first. Even though he won the Nobel Prize in 1951, He didn't make a lot of progress until the late 1950s. In 1958, the Atomic Energy Commission said, yeah, this is a good idea. Let's build a reactor. And who was in charge of that research reactors section at the AEC? It was Alvin Weinberg. Alvin Weinberg took great interest in this project and said, Glenn, he called Glenn up, or he looked around the complex and said, where would I find a reactor design that would be the best? And as Carolyn alluded to, Oak Ridge had a school, the only school of its kind in the US, called the Oak Ridge Reactor Engineering School. You'd come in with a bachelor's degree in engineering or science, and you'd graduate with a master's degree in reactor engineering. Over the course of about 10 or 11 years, there were around 1,100 students that graduated, and every one of these students designed a reactor. So somewhere in some drawer somewhere, there are 1,100 reactor designs. You want to get a hold of those, right? Some are probably good and some are probably not good. But Dick Cheverton, his design was great, and Alvin Weinberg recognized that, and he called Dick up. I think Dick was probably 23 or 24 years old at the time, and he got a call from Alvin Weinberg, said, we love your reactor design, you want to be on the engineering team? Of course, Dick said yes, and in 1958, they started designing, really engineering that reactor. It didn't have a site plan, it was just a concept with a bunch of calculations, and so they decided to site it at ORNL, and they developed those plans in 2 years, and they started digging dirt in 1960. From 1960 to 1965 was the construction phase. And I loved, you think about Vogel and, Plant Vogel and all the other, even Watts Bar plants, and they took 30 years to build. And even then they cost way more than they anticipated. HFIR, I believe, cost way more than they planned. I think they planned for like $19 million and it ended up being, in the mid 20s million dollars, which is amazing. But it went critical in August 1965. It was a brand new reactor design, brand new fuel form, first fuel of its kind, really, in its configuration. I'll talk about that in a minute. But so it took about a year to get up to the design power of 100 megawatts. Operated mostly as a reactor for this transuranium, transplutonium isotope production during those years. And fortunately, on one of the first site visits that Alvin Weinberg made during construction, he came to the crew and he said, I want you to put beam tubes in this reactor. It did not have beam tubes in it. And very fortunately he did, because today that is the primary driver for what funds that reactor. It's funded by the Office of Science, Basic Energy Sciences, for neutron scattering research using the beam tubes. It operated until 1986, when there happened to be some early signs of possible vessel embrittlement, and the DOE at the time said, shut it down. And the way that the reactor and ORNL convinced the DOE to start back up was to lower the operating pressure a bit and to lower the operating power a bit from 100 to 85 megawatts. They fired it back up in 1989, and that's really was the beginning of the increase in neutron scattering work, while still making a wide variety of isotopes. In 2007, neutron scattering introduced the cold source. We call it the cold source. It's a cold moderator vessel that chills the neutrons in one of the beam tubes down so that it can be led to a separate guide hall to do cold neutron scattering research. And I'll talk about that a little bit. Today, we're still operating it at 85 megawatts, primary mission of neutron scattering, but let's face it, the name is the High Flux Isotope Reactor, and it still produces isotopes, still does work for non-proliferation and nuclear forensics, still does nuclear fuels and nuclear materials research. So very diverse. If you haven't seen it, this is basically an image of the vessel, and it is an annular design. So meaning you have the center, the red area is a target region, That's the area of high flux. You have the circle around that is the fuel. The little thin circle that's green or yellow around that is the control region, and then the outer blue region is the reflector region. And there's a diagram of this in the upper right here. So you just get a sense for what is what. We have coolant that comes in. I'll have another diagram that shows that, but it's a light water cooled reactor. It just takes regular water that's demineralized, flows it through the reactor, flows it down through the core, and cools the reaction that way. This will show, I think this will work, how the reactor actually works. These gray and white things, the black and white things, represent cylinders around the fuel. Those cylinders are comprised of a material that absorbs neutrons and keeps those neutrons from communicating with the reflector, which is necessary for all reactors. You have to have reflection to grow the neutron population. It's all about the population of neutrons. So, as that uranium-235 that's in the core, in the fuel, spontaneously fissions, we can change these control plates and open a window for those neutrons to communicate with the reflector. They can communicate and then they can reflect back in, causing more fissions, more neutrons, building that neutron population until it goes critical, and then continuing that until it reaches 85 megawatts, and then maintaining 85 megawatts for however long it takes for those control cylinders to move all the way up and all the way down, respectively. That time varies. Depends on the fuel, depends on what's in the core. It's typically around 24 days. 23 to 27 days is a typical cycle. As far as cooling goes, water comes in inlets at the top of the vessel, passes down through this core, heats up. The water that comes in is about 120 degrees Fahrenheit. It heats up to about 126 degrees Fahrenheit after it passes through the core. Then it goes out to some heat exchangers and chills itself with a secondary loop. That secondary loop chills itself and cools off with a heat exchanger system. Basically, it's cooling towers that exchange with the atmosphere. So it's a relatively simple system. The only system that can get activated at all is that primary loop. And honestly, you can calculate the power of 85 megawatts if you know that this reactor flows about 16,000 gallons per minute and it heats up with a delta T of 36 degrees. So the reactor sits in a pool that's fairly deep within a larger pool that is used for storage of pieces and parts and spent fuel. A lot of parts, it's a 60-year-old machine. A lot of parts get replaced all the time. The outages over the years have gotten longer because more complicated parts have had to be replaced. But fortunately, we've been able to maintain it. It's been able to operate fairly regularly, and we're in a position now where it can operate regularly until we have the next bigger outage.
So Chris, you can see the Cherenkov radiation still.
Yes.
Okay.
Yeah. So these are great shots that were taken, I think, in 2017 or so by Jen Martin at ORNL. I forgot to put the credit on here. But yeah, these are defueling, pulling that fuel element out of the reactor core and the Cherenkov. What I find amazing is the little streaks that are coming off of that. It's not just a glow, there's more happening there. And then even after the fuel is out in that upper right photo, it's still highly activated. You still get a lot of Cherenkov radiation coming from the pieces and parts that are in there. Of course, that decays fairly quickly after you shut down. The fuel stays pretty bright for a month or so, then it cools a bit. These are some spent fuel elements in the spent fuel pool. This reactor happens to use these. We can use these experimentalists can use these spent fuel elements for gamma irradiations, very, very high dose gamma radiations of material samples. And that happens pretty often. I mean, almost all the time, there's something in there getting irradiated in a canister, a specialized canister that was developed to hold samples and keep them dry. And there's an umbilical that you can control electronics that are in there. You can pump gases through that system. Pretty sophisticated system. This is actually a very, very old picture of the reactor control room. If you were to look at it today, almost all these analog gauges are replaced with digital gauges. So many of the systems have been digitized over the past, since I started in 2009, many of the systems have been converted to digital. But it still looks the same. They try to keep the look. In the core itself, there are a bunch of channels that are built into the structures of the reactor to irradiate materials and make isotopes. All these holes and little hexagons are places that can hold a capsule to irradiate it to make something or do something to damage some material. Those are all four of those yellow areas are actually beam tubes. This is a horizontal cross section through the reactor, so through the midplane. So those are beam tubes that stream neutrons out into instruments. And then the green, which are only two of our facilities that basically are like the old bank tellers that shuttle, things pneumatically, shuttle the capsule, but this capsule's about the size of the end of your finger. Shuttle those capsule in pneumatically, and we can put it in and take it out at will. So from 1 second to several minutes or even a couple of days in the outer facility. Into the flux trap, that center region, the high flux region, they decided to put a hydraulic tube. So same principle as the pneumatic tube, but using water. The benefit of the water is, first of all, you get a good cooling effect. You flow water over the stack of capsules. We can put up to 9 of those in this facility, and you flow water over those to keep them cool because they're in the high flux region. Whatever's in that is going to get really hot. I'm going to play a little video here. Hopefully it'll play. And it happens to have a little music. So you'll see the capsules coming out of the reactor. That's coming out of the reactor. And you can see them, the individual capsules. You see the blue glow, the shrink off. That glow is coming through a double wall stainless steel pipe. Doesn't matter. and then now operators are opening we call it the hutch. It's crazy. We call these things rabbits, and we call that the hutch. And opening the hutch to expose the capsules so that they can be put into this tray at the lower right side. And then eventually they'll get shipped. They'll get put into a shipping cask and shipped off to a hot cell. But you can see the types of tools, too, that get used in these. I mean, this is under maybe 10 feet of water. So this is like laparoscopic surgery with big tools, right? No robotic, no Da Vinci machines for this. This is tricky work. And nowadays it's a little easier because the cameras have gotten really good, right? We can get cameras down. It's just this shot alone. And this is a fairly old video. The cameras have gotten way better than this. Resolution and quality of and radiation resistance of cameras. So main research areas. These are the main research areas. I think I touch on every one of these. Let's start with neutron scattering, since it's the primary mission. It's what pays the bills. The three. So you kind of get a sense. I wish the pointer worked. All these squares around the image here represent instruments that are on beam lines. There are 4 beam lines. There are 16 or so instruments. There are 13 instruments that are actually part of the user program. The user program is the program sponsored by the Department of Energy that has 2 proposal calls every year. And if you're a researcher from a university, anywhere in the world, and you want to put your sample in a particular instrument and expose it to neutrons and take measurements, you can write a good proposal. And if that proposal gets funded, you get your time for free. You got to get here. You got to prepare your samples. You have to work with the instrument scientist. Each instrument has a science team that's assigned to it that knows all about their instrument, how to use it, what kind of samples, what kind of preparation is required. And they actually do a lot of the work of each time an experiment is done on one of these instruments to make sure that it's done right and to get the right data. But you can see there are the blue ones, the bluish, are the ones that are in the user program. And the other ones are a little bit more for development. Our instrument scientists found that if we assigned it all to the program, they didn't have any time to work on making better detectors and making better instruments and, trying to put samples in different environments. So we actually do a lot. The neutron sciences group division does a lot of work coming up with new ways to use neutrons and new types of detectors and new methods. So one example is this is actually what we call a thermal instrument. It's a neutron diffractor. And this was done on, I don't have my notes on here. Okay. This was done, we call it in operando. The battery cell was actually, they were tracking the battery. The battery was in the beam line, and they were monitoring it while it was being used and consumed. So they could monitor and understand better the way that this discharged and what happened inside that battery with the chemicals of the battery. This one happened to be a titanium zirc cell, which I'd never heard of until I read this highlight. They believe they've learned enough that they can tweak the design of the battery and make it more efficient. Another one, this is one that is related to a residual stress. So there's one diffractometer in the beam room that can, let me start by, if you were to take when you see an engine, right, an engine block, that's a casting usually. And when you pour that molten metal into that mold and it begins to harden, it hardens on the outside first and then it hardens on the inside next. And so because the inside hardens last, it builds in residual stresses in that material. And that typically causes things to either warp or be more prone to breaking or more prone to warping later. This instrument, this experiment was done on, can map out all those residual stresses in little 1 by 1 by 1 millimeter cubes. So I have seen on that instrument, there have been engine blocks and they've been mapping out. I've also seen railroad railroad track components. But the biggest thing that this machine does now is looks at additive manufacturing parts, because a lot of the metal additive manufacturing is nothing but layers of weld that are put down. And so it's all about optimizing that welding, right? Preheating material before you lay the weld down, or what do you preheat it to, how fast you go, all the parameters associated with this additive manufacturing. They can do this now and monitor this again in operando. So you can watch these things live. Additionally, you can do it post irradiation post fabrication. So you can take the samples that come off a machine somewhere in another state or another city, another research center, bring them over to this machine, and it can analyze the residual stresses for you. You can really, this paper actually covered some software that's used to predict residual stresses and having it compare to the actual residual stresses measured in this machine. And they got good correlation with this new software.
Well, what size sample can be accommodated? I mean, the engine block is a big sample.
It can be very small or it can be very large. But you know, if you wanted to, you wouldn't map out the entire engine block. You'd choose some key locations on it. Yeah, it would take a long time to map out an entire engine block. Yeah. This one has to do, so this is on the cold beam line. So a lot of the work that takes place on the cold beam line, we need to think about cold neutrons, right? When they stream these neutrons through the thing that makes them cold, what makes them cold is a puddle of liquid hydrogen held at about 17 to 20 degrees Kelvin. And when those neutrons pass through that puddle of hydrogen, they slow down. So there are two real good reasons to slow the neutrons down. One is just practical. If you were to put a piece of plastic, a polymer, or a protein, or a plant in a beam line that's just normal, a normal thermal beam line, you just cook whatever. I mean, it would take a second to cook it, and your structure would just be useless. So you slow them down so you don't destroy the sample that you're trying to look at. But more importantly, for neutron scattering, and when you do cold neutron scattering, you really want the wavelength of those neutrons to be on a similar scale to what you're looking at. So in this case, this is about 30 angstrom wavelength coming out of the cold neutron beam. You want your features that you're looking at to be 30 angstroms or so. I mean, within reason. You don't want to be 1 angstrom. So this one is actually looking at some possible drug developments and the mechanisms for some cancers and how they feed. Right. This was an extension, not an extension. This was a follow-on to some really interesting research on actually COVID-19 that this beamline did to understand how COVID multiplied and spread. So a lot of practical applications with respect to drug development and disease understanding. Then we move to radioisotopes. This is my area. So these are radioisotopes that we currently produce at Oak Ridge. It's a pretty long list. Carolyn alluded to airport surveillance. Nickel-63 is used in electron capture units. If you go to the airport and they swipe your bag and they stick it in a little machine, it's probably, there's a good chance it's a nickel-63 source in there that's zapping it to do electron capture detection of, explosives and other things. I'll talk about a couple of other of these as we go, but it's a big list. And that list is growing. There are several items on there that I wasn't going to talk about today, but that we're working on actively, mainly to address the supply issues caused by the Russia-Ukraine conflict. So to start off with, and you mentioned element 117, tennessine, there's been a lot of work that has gone on despite not being able to work with the Russians. So Russia was key in element 117 discovery and element 118. There are not that many facilities in the world that are set up to do what they do in Dubna. But there are some. And I will say Lawrence Berkeley Laboratory is able to do some bombardments. Most new super heavy element discoveries come from a target material being bombarded with a heavy ion, right? So in the case of element 117, it was berkelium-249 being bombarded with calcium-48, right? So, and that produced element 117. Right now, we have supplied some material to the Japanese in their accelerator and to Lawrence Berkeley Labs to do different bombardments. For instance, californium-249 target being bombarded with a titanium-50 beam to hopefully get element 120. This has not been done yet, but it's hopeful. And then a curium-248 target with a vanadium-51 beam to produce element 119. So there is active work in this. It's just not with the Russians at this point. There will come a day when we can do that again,
Well, tennessine is a halogen.
I guess.
It's in the chart.
That's where it is in the chart. Yeah, I think prove it.
So, of a nuclei that they found.
Yes. Still a big HFIR still is a big producer of californium-252. Since there are only two places on Earth that make it, SM3 in Russia and HFIR, our business is booming. So DOE's business is booming, and we are providing the material. Of course, it's used for reactor startups, brand new. You got a cold core. You need something to get it kick-started. It's used for well logging, and it's used for real-time. I think Bull Run used this for years. Real-time coal analysis, where you've got a californium source and a detector below the conveyor, and you're just monitoring sulfur content, right? Because you're limited. You got to limit your sulfur content. So they would just divert it. If they saw high sulfur content, they divert that thing to a different location. And then of course there's plutonium-238. So this has been a pretty, I feel like this has been a really successful project and program. We have increased production significantly since the early mid 2010s. We were able to get some material on the Mars rover Perseverance from HFIR. The Mars rover Curiosity did not actually include any material from HFIR, but we were just a hair late. Like we had made the shipment, but those radiothermal electric generators were already being assembled. But we were able to get some material on the Perseverance. So that was part of the Perseverance payload, at least. That happens at a combination of labs: Idaho National Lab, Oak Ridge National Lab, and Los Alamos all participate in that program. So the next time you're probably going to see a mission using our PU-238 is the Dragonfly mission, which seems to be getting traction and may actually get funded. That's the helicopter mission that'll be flown on Titan, Saturn's moon, one of Saturn's moons. I'm not positive, but I think it might take more than one normal RTG. It might be multiple radiothermal electric generators to do that, but I don't think they have a design completely done yet either.
How much do you produce? What's the quantity of PU-238?
I can't say.
Originally planned to the improvements you say you got.
So for a while, we were producing about 200 grams per year, which is good. It's a good amount. That's not what we had anticipated. The goal is about 1.5 kgs per year. The PU-238 that's produced at Oak Ridge is not really, you got to think of it as kind of a spike, right? There's a stockpile of plutonium-238 that is decaying as we speak. And at some point, it decays below its usable activity. What the stuff that HFIR produces, and the Advanced Test Reactor in Idaho is also doing irradiations to produce it. The stuff that we produce is high enough quality that we can spike the existing stockpile and get that quality level up so that they can produce the 100% power radiothermal electric generator. We're not going to take this. I mean, the stuff we make is really good stuff, and we're not going to use it all in one RTG. We're going to spike the existing stockpile and stretch this out as much as we can. Nickel 63, I talked about this already. It is produced, well, it used to be produced in these very long targets, and we transitioned about 6 or 7 years ago to smaller targets just for flexibility. It's hard to ship these. It's very, very easy to ship small capsules in an ORNL. It's a lot more difficult to ship the long capsules. It requires a bigger shipping cask. It's just a lot of work, costs more. I mean, we could do it, but we've gone to the small capsules. It just makes fabrication easier and everything. Still make selenium-75, make a lot of it. It's used for mostly weld radiography. It's a great gamma radiography source. We also, you may have seen headlines, we restarted what we used to make in the 90s, which is iridium-192, which is another great similar use, weld radiography. So great progress on that, reestablishing that production. And then, of course, we make medical radioisotopes. We make actinium-227. That was the first one that was used in an FDA-approved product from Oak Ridge called Xofigo. And it's actually radium-223, which is a daughter product. But that was intended for late stage, it was intended to be palliative for late stage bone metastasized prostate cancer. Because, prostate cancer can metastasize typically to your lymph nodes or to your bones. If it goes to your bones, and when you have bone metastases, you're in pain. It was meant to be a pain treatment for late stage bone metastases. It turns out it was actually pretty successful at treatment. So they've been working on new label guidance and trying to get it approved for other treatment uses instead of just palliation. Actinium-225 is another interesting one. It can be made in HFIR. We can produce the thorium-229 that is used to generate actinium-225. It's also used as found in by other sources. There's thorium-229 from other legacy material that can be used to make to what we call milk actinium-225 from. It's another one that's really being looked at as a targeted alpha therapy. So it decays by alpha emission, just like radium-223 does. But they've had a little bit more success actually connecting that actinium-225 to targeting molecules that carry this to certain places in your body. And then another big one is lead-212, which, similar to actinium-225, is used as an alpha therapy, targeted alpha therapy, and it is even more. It has a better affinity to these targeting molecules and is easier to carry in the body to different locations. So there's a host of new ones that they're being looked at. Not sure if HFIR is going to be involved in making those. Some of those might be made at medical cyclotrons, at medical centers, and elsewhere. But a lot of really interesting work in this area, and between this and immunotherapy. I mean, the combination of those two shows a lot of promise for cancer treatment in the U.S. Of course, HFIR can damage material faster than most places, right? HFIR does it supports a lot of research that extends life of existing power reactor fleets. When a power reactor says, I want to get a 10-year extension, the NRC says, prove that these materials are going to be okay in 10 years. Well, HFIR can test a sample of steel and do 40 years of damage in a year and a half in the reactor. So we can really get ahead of it. Like, we've done a lot of work for the Canadian Nuclear Regulatory Commission for some of the CANDU reactors, trying to get them to get their license extensions, as well as other applications like ITER, the first fusion, one of the largest fusion experiments. We can do a lot of damage testing of ITER components to see how tolerant they're going to be and how damaged they're going to get. And then we can also do fuels irradiation. So we kind of lump these all together, fuels and materials, they're all materials. So we can really kind of dig into all three of these areas. And there's a lot of activity going on because of all the next generation, these new small modular reactors, they have to do a lot of testing. So there's a lot of work that HFIR can do to support that. And then, of course, the NAA capabilities, using those two facilities for nuclear forensics. We have those two facilities have very different characteristics. One of them is pretty inward on the core, and it's kind of close to the fuel. So it gets pretty hot. We can't leave, we have to put samples in little in graphite capsules so that the capsule doesn't melt in there, and we have to be careful about what we put in that facility and how long we leave it. And the one that's way outboard of the reactor, the much lower flux facility, we can use plastic little polyethylene capsules that just have little screw tops on them, and the sample goes in there, and we can leave it in there for a little longer too. But very useful. Carolyn alluded to the Zachary Taylor work that was done. That was done in it's actually not done in HFIR. It was actually done at the Oak Ridge Research Reactor, but that system essentially got moved to HFIR when HFIR at some point, I don't remember exactly when that was, and so it's very similar work that we've done. We've done work analyzing materials for maybe like marine estuaries, seeing why where are the heavy chemicals that are in there, or heavy elements that might be in the marine estuary damaging some of the ecology. We've done work with the FBI and with the police forces. There's a lot of really interesting work. And of course, the International Atomic Energy Agency is a big customer of this facility, doing pre-inspection checks on samples that are gathered from around the world. And then our gamma facility, which we've done this is just a short list. We've done some work for NASA. We've done some work on ion exchange resins to see how radiation tolerant they are. We've done some work on ITER. So ITER has this big conductor coil that goes around it to create the magnetic field to confine the plasma that's heating this up so greatly. And we can test those sections of that in the gamma facility under 20,000 volts of 20,000 volts voltage. And then we've done some work with the FDA on spinal implants and disc replacements that use just polyethylene material, but the manufacturer of these use radiation hardening, and the FDA didn't believe the 8 different stories they got from 8 different vendors on what kind of dose rate made the optimal hardness on these disc interfaces. So we helped them out. And then the final one for the applications is neutrinos. So neutrinos, you may have heard of neutrinos. They pass through everything. You have like 10 to the 15th neutrinos going through your body every second right now, right? They just don't interact with matter. And they don't interact with matter often. Actually, if you wanted to guarantee you stop a neutrino, you just need 1 light year of lead. Kind of a crazy, I like thinking about that. That's really crazy. But they do interact occasionally, and HFIR produces a lot of neutrinos, on the order of 10 to the 19th per second. More neutrinos than they do neutrons. So in the late mid-2010s, I helped this collaboration. It was a collaboration of 13 institutions led by Yale University, and they wanted to put a detector in the experiment room kind of close to the reactor core. So they were about 7 meters from the reactor core. So we did this. It's a 10 by 10 by 10 detector. It has a liquid scintillator in it, and they were able to get about 100 clicks of neutrinos per day, which is pretty good. They left it there for a month. They got some reasonable statistics. Their detectors started failing at some point, just not working. The electronics quit working. And so they pulled it out. They're actually working on a second version that I think they're going to try to put in soon. The second version won't be liquid scintillator. It'll be a solid material. So big projects coming up. First one, it's going to happen in around 2029. They're going to replace the permanent beryllium. The permanent beryllium is the large piece that's on the outskirts of the reactor core. It's a single piece. It's a complex machine product. It's a material that's not fun to work with. There's one company in the United States that can actually machine this. The ingot was purchased 10 or 12 years ago. from the one company in the United States that makes it. And then it's actually being machined now. So that's positive. You can't just replace the beryllium reflector. You do way more than that. It's called a beryllium reflector outage, but so many other parts are changed with the reflector outage. One of the things we did in 2018, 2019 was we said, hey, if you're going to replace the beryllium reflector, let's change the configuration a bit. We can make more plutonium-238 and we can offer more irradiation sites, and we can reduce the stresses in this because it wasn't designed optimally. It was designed in 1958 with a slide rule and paper. Actually, it was probably designed in 1956 or 57, and Weinberg noticed it in 58. But what we've done is we've taken all these sites and we've added some and reconfigured them so that we get more usable sites. There are actually a couple in the current configuration. We can't really use them. They're either too close to a beam tube and they perturb the flux in a beam tube, or they're blocked by some piping, which I don't understand how that happened. But so now in the new one, we've gone from 22 of those, only 18 were usable, up to 28, in which 28 are usable. So much better, and we have improved the thermal management of that beryllium so that during the cycle, when you operate the reactor, it comes up to a temperature and then it goes down when you turn it off. And so you go through all these cycles of this thing, and we believe we've improved the stress levels in this revised design so that the reflector should actually last longer. We can't prove that until we run one, but
What temperature does it get to?
not super hot. Maybe. I took that out of the slide just to save space. There is one plot that has the temperature plots, a couple hundred degrees Fahrenheit. It's not super hot, but it's enough. The cycling is what really causes the problem. There are some other plans for the beryllium outage. We want to change the guide hall. This happens to be a layout of the cold guide hall. The cold neutrons come out of the reactor and go out into this guide hall. And we're going to change the layout, change some of the guides in the tubes. All the beam tubes that are in that reflector, they come out and they have to be replaced. So we get all new beam tubes. We can change those beam tubes a bit. That's some of the plans. We're going to change one of them. And so there are options. We've had the option to take this opportunity to make some of these improvements to the cold source beam tube and to the guides that guide things out to the instruments themselves. So during we were going to do. I think we were going to do during the beryllium outage a bunch of work. And when they started getting into the plans, they decided, okay, well, let's separate this out and do this in a different outage, and that'll keep our beryllium outage, as short as possible. So I believe for now, the plan is to do this cold source helium compressor upgrade prior to the beryllium outage. That's probably subject to change, but this is a limiting factor. The current cold source helium compressor system, which keeps that liquid hydrogen at 17 to 20 degrees Kelvin, it's a complicated system. There's a lot to that system. It's probably about as complicated as the reactor itself. And these compressor systems, when they designed this, they chose a piston style compressor, which was fine at the time. They were fairly reliable. They do require a lot of preventive maintenance. In fact, every year, twice a year, these have to be taken down, and once a year, these compressors need to be fully rebuilt with all new components, all new pistons, all new rings. It requires that the reactor has outages that are 70 to 80 days long twice a year. So if you think you want to operate the reactor more operating time during the year, right? Ideally, what would be nice to be able to get 8 24-day cycles in every year. Right now, it's doing between 5 and 7 of those cycles. Can't quite get to 8. Not really possible to get to 8 with these two large outages. If we replace these, when we replace these helium compressors, they're much more reliable. They'll be they'll have turbine expanders on them, and they're gonna eliminate those long outages. And that this is a possibility for 8 cycles for this reactor, given that if we can get the fuel right. So that's key. But this system is interesting. It uses liquid nitrogen to cool the compressed helium, and then that helium exchanges heat and cools the hydrogen. So it's basically a 3-stage system, very complicated, and you're dealing with helium, or you're dealing with hydrogen. So you've got flammability issues and oxygen depletion issues related to that in the building. So there's a lot of complexity to the systems that are in that reactor building. So this just shows you some before, the refrigerator system. We're going to increase the capacity of it from 3,500 to 4,500 watts. And then we're going to change it to a regular PLC controlled system, which we can find instrument controls for people that can program. Like the one now is very difficult. And then the new one, we're going from a screw type compressor to a turbine type compressor, and put variable frequency drives on it. Sealed. Right now, oil contamination is a huge problem. That will be a thing of the past with the new system. So simplifying across the board. And then, this is the same thing. You can see the replacement parts that are down there in that lower image. And that is the expansion engine that has to be worked on and rebuilt once a year. We're also planning, and I'm on the team for this, planning a pressure vessel replacement, which will probably happen sometime between 2035 and 2040, somewhere in that range. It's early in the planning process. It is an improved project so far by DOE. They realize that they want this reactor to operate beyond the year 2100. So much that they put together a scientific committee to evaluate the high performance reactor based research facilities within the Office of Science, which there's one. It's HFIR. So and they determined and recommended that we address the life limiting issues, which is the vessel, which will be embrittled and probably beyond its design life in the 2060s. But why wait to start that planning? Why wait? The longer you wait, the more uncertainty there is that maybe your embrittlement calculations are wrong. And, let's think about getting it done sooner than later. So we also have an opportunity, and they recommended that we enhance the scientific facility infrastructure. So what can we do when we replace a vessel? And when you replace a vessel, you replace everything else that's in the vessel. What can we do to make life better and bring new capabilities to the lab at HFIR beyond this replacement? And then they asked us to attempt to coordinate with LEU conversion. So, they're not joint projects, but we're not going to preclude that from happening. So we have a CD0, which is their, kickoff, basically, mission needs statement from DOE saying we can proceed. And there's a couple images of, you saw the one of the pool and the reactor in the pool. This is one of the reactor itself, the vessel itself. The vessel has that long snout at the bottom that goes into the sub-pile room below it that has a control system. So there is a lot that needs to be replaced with this. It is not a trivial task, but it's also doable. We know that because we have benchmarked other facilities that have decommissioned or replaced steam generators and power plants that are much, much bigger than this. Yes, it's radioactive, but so are a lot of these other components that have been replaced at other facilities. So it's possible. It's just a matter of how and how long it's going to take. We know we're going to replace the vessel, which is carbon steel that's clad in stainless. We're going to replace it with some form of stainless steel, TBD, what grade and what type that is. We know that DOE has asked us to be able to operate at 100 megawatts. Doesn't mean we're going to operate at 100 megawatts, but it needs to be capable of that. Also, we want to make the interfaces with the beam tubes flexible enough that we can actually change size of the beam tubes sometime, maybe 30 years in the future. When somebody says, I want a larger beam tube, or I want to change the angle of that beam tube by a couple of degrees, that it's flexible enough to do that. And we know that we want to make some changes to the vessel head design that improves maintenance, make maintenance easier, that makes irradiation of for isotope production and materials easier, and enables some other possibilities of online insertion and removable, kind of like that hydraulic tube did. Other facilities that we can put capsules in and take capsules out at will. So there are a couple other interesting things that are happening at ORNL. I thought I'd just throw them in here. There is an active project to build a new hot cell facility called the radioisotope processing facility. Without HFIR, you don't need to do this. But because we're making a lot of isotopes these days, and it doesn't look like it's going to be decreasing and only increasing, we really need modern facilities to process these radioisotopes and send them out. So this is really important to the laboratory and really important for HFIR. And we have really good support from DOE on this. And then another one that is almost, it had a ceremony last week. They called it the topping ceremony, where they put the top beam on the building, which is the Stable Isotope Production and Research Center, which is an enrichment facility. Which, why do we care about that? Well, a lot of the radioisotopes we make start with enriched material, and without that enriched material, we don't get those. So the enrichment capabilities, which lie in the same directorate, the Isotope Science and Enrichment Directorate, all work together. It's a very vertically integrated system that we have. And that is it. And I'm happy to answer questions.
That would be down.
For the beryllium outage?
Yeah.
The current plan is to try to stay down less than 1 year. That changes. I mean, I think that's the current plan. I don't know what the future plan is going to be. They're still working through the schedule. And as you can imagine, a lot of components, hundreds of components get replaced and are being manufactured now. And the manufacturing in the US is not at its peak. And so there are active efforts to try to, there are some parts that the lead times are just tremendously long for. So they're really working with those vendors, trying to get lead times shortened. And so that's driving a lot of it.
So the core and the new beryllium filter would then just be dropped as a unit into the new pressure vessel.
Not as, for the pressure vessel replacement? Yeah, the goal with a pressure vessel replacement would be, we would build a separate building that replicated the pool, but was dry. Even the subpile room, everything would be like that as it is. And it would be everything, all the parts would be brand new and would be assembled in this cold setup. We knew everything fit, then we could take it. You can't take the entire thing and move it over, but you can take it apart and put it back together again in the actual pool and know that it fit once, it's going to fit again.
How long is that? I mean, how long is the outage for the pressure vessel?
We don't know yet. It's probably 2 to 3 years, but we don't know for sure. It's not fully planned out. That's in approaching 2040. We're in the early stages.
you have plenty of storage space for these used parts that are being generated?
We do. We've been shipping fuel frequently and cleaning out the pool regularly. So there seems to be enough room to handle the beryllium outage. We should have plenty of room. Pressure vessel replacement, again, it's early on. We don't exactly know how much storage space in the pool we're going to need for that. We don't know what's going to come out of the pool and just get shipped immediately, and what's got to stay in the pool for a while yet. We're still working through that.
I understand NASA has, about a month ago, dropped their funding for plutonium-238 sources. How does this interface with DOE and their sources? I mean,
Yeah.
that's the primary use for it, I thought.
They didn't drop our funding.
Okay, you'll make it whether anybody uses
They
it
kept
or
our
not.
funding, so I'm not sure what they dropped.
And related, apparently it's made from Neptunium-237.
Correct.
And I thought that was abundant because of the weapons production, which is more or less stopped. So I thought that source is sort of depleted. Is there a bunch in stockpile you use?
It's not depleted, but it's not unlimited. There's
Well, I
plenty.
mean,
There's plenty.
They're not, I understand they're not making it anymore.
Right.
But there's a stockpile of it. Is that-
There is.
Okay, so.
Yeah, we have enough supply and we do. And remember, when we irradiate Neptunium-237 to make Pu-238, only about 10% gets converted to plutonium. So and then maybe another 5 to 10% gets fissioned away. And so there's approximately 80% of it left to recycle. And we do recycle the Neptunium. So it'll take us a long time to get through the Neptunium in stock. I mean, decades and decades.
Is the spent fuel from HFIR reprocessed?
It currently goes to Savannah River site and is put in a pool. Used to be that, there were times when it was run through H Canyon and used. I don't know if that's still happening or not. I'm not sure.
This is just remarkable to me and to many. 20 years ago, when I was at the lab as a deputy director, there was genuine concern about HFIR being shut down because SNS was coming up. You need HFIR for the long future. So this is remarkable.
We think so too. We're very glad that that DOE recognized what a treasure this machine is and funded it appropriately and has really taken. I mean, I think honestly, radioisotopes over the past 4 or 5 years have really helped make that case. There is nowhere else to make these.
Since you said you gotta build a new box to try everything together, might it be easier just to build a new reactor as opposed to try to refit the new parts of the old building?
Sounds great. So yeah, new reactor would be wonderful. When Idaho tried to build a new reactor 3, 4, or 5 years ago, the cost crept up and up and up to $5 billion. So nobody's going to spend $5 billion on a reactor. I'd love it if they would. We all would love it if they would. It would be better to keep HFIR running, build a new reactor, have 2 reactors until the 1960s when you can transition over to the new one completely. I mean, that would be ideal. But practically in today's current environment, we're not going to get $5 billion for a reactor, unfortunately.
Some of these new reactors, they're looking advanced reactors are fast neutron reactors because can HFIR help in that area, since it's a thermal neutron reactor?
Yeah, we can. Many of the neutrons in the flux trap are fast neutrons. So actually almost all material damage to samples kind of requires that you filter those thermal neutrons and only allow the fast ones in. So a lot of material samples that get put in capsules are surrounded by a filter, but maybe that's gadolinium, maybe that's europium, maybe there are a series of elements that are good at capturing those thermal neutrons and only letting the fast ones hit the sample. So yes, we do work. That's like fusion, right? Fusion, those are all high energy, 2.4 MeV. So or higher. So yeah, we do a lot of work with fast neutrons. Let me get.
I don't know if anyone can follow it. But they also have anything to do with the bomb that we sent to Iran.
I have no idea if
Somebody that made bomb.
yeah, I don't know. It wasn't a nuclear weapon, so I don't think it had anything to do with ORNL. And not that we do nuclear weapons work, but Trent.
Not a question, but it's a story that I think you may be interested in. I worked at HFIR for quite a while and met Dick Shepperton, and he called me up from time to time, wanting to know what was going on. And the first time he called, he of course introduced himself, and he said, well, I'm gonna tell you this story. He said, I was working at Oak Ridge, and one of my friends called me and wanted to go to reactor school. That's what he called it, reactor school. And he said, he wanted to know how to get in. And he said, oh, don't worry, I'll get you an application. I'll send it to you in the mail. So he called up whatever office it was that was handling that and said, hi, my name's Dick Shepperton. I'd like to get an application to reactor school. And the woman said, okay, Dick Shepperton, okay, written down, okay, I've got you ready to come in. No, it's not for me. It's for my friend, Mr. X. He said, I know you want to come in. I know that's the real reason you're calling. I have you on the list. And he said, ma'am, I do not want to go to reactor school. I want you to send it to Mr. X. She said, you're on the list. You show up. It's on such and such date. I'm sending it to you. Yes, it's just. It's from Dick.
That's a great story. I like that.
And this is a Zoom question.
Oh,
Are there plans for an independent spent fuel storage installation for HFIR? And also, is the waste being processed through vitrification? And are there plans or programs investigating how to utilize the HFIR waste?
so there is a plan to dry store HFIR fuel for the long term, not eliminating the need to ship it to Savannah River. The other, I don't know what other waste they'd be talking about. There's a lot of waste related to radioisotopes. Most of that is transuranic waste, and that is handled separately and differently, and there are pathways for that. But the rest of the reactor, most reactor components can just be buried. They're not, I mean, steel and aluminum, and they don't need to be vitrified, or they're just hard pieces that can be buried and shielded. Phil?
So since struggling parts of the reactor, is there any thought of changing the fuel plates?
We've thought a lot about changing the fuel plates. Some of the people on this team that I led and I'm leading would love that, but that's probably a bridge too far. You really need to limit the scope of this. That could be a separate project. It could be really interesting. And we talk about it all the time, changing the fuel design. There are some possibilities for improving the HFIR cycle, mainly the cycle length. There are some possibilities for, improving the fuel performance, but we treat those totally separately. Yeah.
Since you mentioned that, converting it to lower halo fuel, what's the probability, or how does that fit in with your current concepts?
I would say the reactor conversion probability looked good until a couple of months ago, and basically the big beautiful bill zeroed it out. So we don't know where it stands, right?
To study radiation damage, you have to have a sample in place for like a year or more.
We can do radiation damage testing in one operating cycle and get meaningful results, for some cases. Yeah, 24 days. And then you have to ship it to a hot cell and do a bunch of tests on it in a hot cell facility. But yeah, you can get meaningful results. Just depends on the sample, what you're looking for, and what kind of damage you're testing for. All right. Thank you.
Thank you for an excellent overview. I'm an English major and understood a lot of it. I can't operate a reactor or anything, but I wish we had baked you a birthday cake shaped like a pressure vessel with 60 candles. But I do have a cup for you.
Oh, hey, all right. You know what? Who doesn't need another coffee cup? Drink it every day.
Okay, good.
So, thank you very much.
Thanks so
Appreciate
much.
it. Thank you.
Yeah.